Bene, we can start. Good morning, on this nice day, or bad day for you. Comment on the news of the week. Any question on the directional coupler? No question on the directional coupler? So everything is more or less fine. So we introduced the couplet mode theory, the detail. We applied to this condition, so two straight waveguide close one to each other, close in the sense of the evanescent tail of the field of the mode that is perturbed by the presence of the other waveguide. This can be described as the two mode of the structure, the symmetric mode on or the anti-symmetric mode, both with a different, as every mode, propagation constant. You can think this as a combination of the two modes of the waveguides. So if you enter from one waveguide, you have a pattern, a field pattern like this. It seems that the power bounces up and down from the two coupled waveguide, and the periodicity of the two waveguide of the exchange of power is related to the coupling coefficient, and more in general, in case the two waveguides are different, also from the phase difference, so the phase mismatch between the two waveguides. In terms of the delta that I introduced in our formula is the period of this exchange of power, and can be clearly written as the difference of the phase constant of the two modes of the structure, so the symmetric mode and anti-symmetric mode. I'm doing just a summary of the previous two lessons. Okay? So it can be written like this, or can be written like this. Take the expression of the eigenvalue, the first eigenvalue that we calculated, and if you do the difference, you get exactly this. Someone ask me about this region. This is the capping region, and we have a very good formulation for this part, but then you have to arrive in this condition. So from this faraway condition where the waveguides are not capping to this. And clearly, this is a transition region that has an impact on the behavior of the coupler. This is a more fine description of the coupler that we can neglect. You can imagine that this part give you a residual coupling that in a very accurate design you have to take into account, but it is not necessary at our level. The coupling coefficient depends, is proportional to the exponential decay of the field, so the coupling coefficient is proportional to an exponential function of the distance between the two waveguides, or the gap between the two waveguides. So it's strongly dependent. And then we introduce the coupling coefficient. So if you think the coupler like this, you enter here with a given power, P0, and you exit with, you split the power in two, and the ratio P2 over P0, or if you want to take into account the attenuation, the sum of the two, is the coupling coefficient, the power coupling coefficient. The small k is the field coupling coefficient. This is called the field coupling coefficient, and this is the power coupling coefficient. Usually, people refer to this port as bar and this one as cross. Cross because you cross the directional coupler and you go to the other port. Bar, you go on the same port. The insertion loss is the ratio between P1 plus P2 and P0, so the difference between basically what is lost in the coupler. To be, well, more correct is P0 minus these two, so what you lose in the coupler, that is the insertion loss. Okay, so in case of no coupler, P1 plus P, in case of no loss, P1 plus P2 is P0, and so this ratio is 1 or 0 if you consider it as usual. What else? Then we introduce the transmission matrix of the coupler. This is very useful because you describe this object just with a matrix with 2 input and 2 output. So you summarize the entire behavior, the entire electromagnetic behavior of the coupler in just one matrix that relate the output complex amplitude of the field to the input complex amplitude of the field. And this is extremely convenient, because if you have to combine various building blocks, you want to cascade, then it's very easy. You just have to multiply the matrix together. So very easy, very easy, very simple. This is the general expression, complete general expression that takes into account the insertion loss, that takes into account the phase shift due to the physical length of the coupler, and takes into account also the asymmetry of the coupler. This matrix becomes much simpler in case of a symmetric. Let me see if I have. No, I can write. In case of a symmetrical coupler, so with a 2 waveguide, with a 2 identical waveguide, is cos CL or KL minus J sin, and here we have minus J sin and cos. So this is the transmission matrix that describes the behavior of your coupler. And with this, you can calculate every output once the input are known. So very easy. We have seen that the transfer function is periodic, as you can see from here. And the other point that we notice is that you are not, in the formula always appear the product CL. So you cannot calculate the length, if you want to do the design of the coupler, you cannot calculate the L or the C. You have to impose one of the two and calculate the other one. So if you wanted to realize a 3 dB coupler, so a coupler that's split in two, you need this one as 1 over square root of 2. So we need the CL equal to pi divided by 4. So now, depending on your technology, on your waveguide, on your ability to put the 2 waveguide close to the other one, you can decide the field the coupling coefficient. And at that point, you can calculate the length of the coupler. This is the design of the direction of coupler. Is it okay? Is it clear? Very simple exercise. Assume you have you want to design a coupler that works in cross. So the coupler, you enter from here, let's say with a P in or P0, and you want to exit from here. So you don't want to exit from here. So it is 100% you can do this only if delta beta is equal to 0. So a synchronous coupler, because if it is not synchronous, you are not able to couple 100% of the power. So this is the first part of the design of the coupler. The second one is, okay, delta beta equal to 0, so the transfer matrix is this one. So I want this one equal to 1, so C multiplied by L equal to half pi. So, okay. If C multiplied by L is half pi, this term is equal to 0, and this is equal to 1. It means that you are exactly in this condition.
Why sine CL is equal to 1?
Why?
Why this function is a matrix equal to 1?
Because you wanted to realize this condition.
Why
The P bar is P cross, sorry. P cross is PC 2, 1 to the square. Yes. So you want the transmission equal to 1 on the cross, and you want the P bar that is equal to the first coefficient of the matrix equal to 0. So both relation, we wrote the two here, two conditions, but the two conditions are identical and they bring to this result. CL equal to half pi. Now the question is, how well you have to control the product CL? It is clear from an engineer point of view that if this is a nominal condition, but you never reach this. Zero does not exist in our world. Is a small number, but it's not 0. So assume you accept here every power lower than 25 dB, the condition. So if the power there is lower than minus 25 dB, is acceptable. Can be 30, can be 20, can be 10, can be 60, depending on your application. So which is the tolerance on the CL product? Uh, 25 dB is equal to 3.1 times 10 to minus 3. This means that the cos square of the perturbed CL, I don't know, C first, C prime and prime, is equal to 3.1 10 to minus 3. It means that this perturbed CL is equal to let me see. This can be 151.45 or 162.70. So means half pi plus minus 3.7%. So you have to control the product with a precision, an accuracy of 3.7%. If this one stay in this range, the output power is lower than 25 dB. That for our application is 0, is acceptable. This means that you have to divide this tolerance on these two terms. Usually L is very well defined. It's defined in the lithography, with the lithography, so it's absolutely correct. When you make it, L is the good one. So typically L is the right one. I remove the prime here. So the problem is on C, because C is the field coupling coefficient, and the field coupling coefficient, you know, that is, you remember the expression is K0 to the square divided by beta, the integral of psi1, psi2 delta n. If I well remember. I think it's correct. And yes, there is a. The 2 and pi, I always forget in the formula.
Square. 10 squared, delta n squared.
What is important is, you see here, a wavelength dependence. Two is 2. Does not depend on technology, does not depend on frequency, does not depend on temperature, does not depend on the solar wind. So 2 is not important. What is important is this one. That depends on beta. Beta, what is beta? 2 pi divided by lambda and the effective index. So this depends on the width of the waveguide. So if you make an error on the width of the waveguide, immediately this will change. So K change, so this condition is affected. Depends on the temperature. Depends on the technological process. Depends on a lot of things. If you think to space application on satellite, it depends on the radiation. There are a lot of radiation out of the atmosphere. So, and it depends on the wavelength. So I have to expect that this design is for a given wavelength. And if I move from the design wavelength, C change, and the risk is to move outside of this condition. And also, this part depends on what? On the shape of the modes. And the shape of the modes depends on the waveguide. That depends on the temperature. That depends on the polarization. That depends on everything. So, you see, with very simple consideration and formula, we arrive to the accuracy that we want. But then, move from this number to the real control of the device is another job, and it's a difficult job. Because from this number, you get information on how well you have to control the temperature. The refractive index depends on the temperature. How far you can go in wavelength. How well you have controlled the technology, because the waveguide is responsible, waveguide shape and refractive index is responsible for the shape of the mode, etc., etc., etc. Okay? This is the, let's say, difficult part of the design. Is really the art behind the experience of the designer in every field, and in this case in integrated optics. Is always like this in our field, in your field as engineer. So the ability to understand which is the responsible of this and how to control it and how much to control. Because the control means money. No, it's easy to say, well, let's control the width of the waveguide with plus minus 1 atom. But this costs a lot. And your product at this point costs too much. No one buy your product. And that's the problem. So this is the real importance of this analysis. Okay, some philosophy, and let's go back to our exercise. We have a periodic function here. Okay, so I say the CL equal to half pi. No one reacted, but I could write also half pi plus 2 pi. It's the same. If I impose a CL equal to this number, well, I'm still in this condition, 0 and 1. No problem. Or multiply by n, an integer number, it's the same, no? I can do it a very long coupler that perform exactly the same. Is the same or not?
No, it's not the same.
It's not the same. Why?
Because the other modes proteins too long.
No. The first answer was correct, but not the second one.
Because the device becomes bigger.
Yes, and usually we wanted to pack and have a small, so this can be a good reason, but if it performs better, maybe it's better to get it longer. But
Your coupling ratio gonna decrease a lot because it has a limitation of product.
no, this number increase, this one. You can keep C constant, always the same waveguide, same distance, same gap, and just increase the L.
Then we don't have any benefit of increasing the L. We are achieving the same at pi by 2.
We don't have any benefit, we have only detrimental effect, because if you do again this calculation, now with this condition, this number remains the same, but this one is larger, so what we get here is, as an example, if you do 2 pi divided, sorry, half pi plus, so it's not a 2 pi, but is pi because the power goes with the square, so plus minus 1.2%. So this number is larger, so the absolute control is the same, but the relative control is lower, obviously. Pi times lower, so roughly 1/3.
The longer it is, the easier it is to control it. But
No, the opposite. The longer it is, the more difficult it is to control. It becomes more sensitive. It becomes more sensitive to everything, because what we said before is 3 times worse now. If you have a perturbation of effective index for some reason, because of the aging of the device, because after 20 years in the field changed. So if this one changes for some reason, you get out from this condition sooner than this, because the number is smaller. So it's more critical.
Could you please repeat how did you find this product CL perturbed, new one, this new occurrence?
This one,
New one.
exactly as this.
But which?
So you have cos square of the new one
Okay,
uh,
I got.
equal to this number.
Mhm.
So you have this is the square root CL is the square root of this, and then you have to cos minus 1. But now you take the second solution, so you add pi to this one. So just this number plus pi. So this exercise is to say that you have to choose the first solution. The shorter, the better. Is less sensitive to everything that can influence on this expression. Wavelength, effective index, shape of the mode, perturbation, so the waveguide, and so on.
What is that? Also, the shorter waveguide, I mean, longer waveguide has a more loss than shorter, right? I mean,
This
this
is
one
another
of the
reason
like
to-
microwave system. I mean, when the transmission line is increasing, so we are, I mean, losing the power a lot. So
This is another reason to make the device shorter, even if this device can be tens of hundreds of micron long. And most of the loss come from the transition region, not really from this part. Okay? Good. We mentioned in this discussion, we mentioned another important point, that is this one. Another important point is this one. Dependence on the wavelength. This is the model of the directional coupler, a circuit model. But the physics is behind the geometrical dimension, the physical property, the refractive index, everything is inside. The electromagnetics is inside the model, hidden basically in this C. And the expression is, we have found on Monday, and is this one. So the coupling coefficient C is not just a number, but is a function of the wavelength. So you can write, for example, this. You can assume this behavior. We have here K0 is 1 over lambda to the square, divided by beta, that is 1 over lambda. Okay, and then you have the integral. The shape of the model depends on the wavelength, and there is a product, so to the square. The larger, the higher is the wavelength, the larger is the mode. The mode of the waveguide increase by increasing the wavelength, the shape. You remember, is the wavelength increase, the mode is less confined, and so the mode becomes larger. Now, the coupling coefficient depends is an exponential function of the distance. Okay? So if you increase the wavelength, this is the other waveguide, you see that the evanescent field inside the waveguide increase. So if you increase the wavelength, you increase the coupling with an exponential function. So the exponential function cancel this term. You can say that this depends on lambda to the square. So C is proportional to lambda at the end. So this can be a good approximation in wavelength of the coupling coefficient.
When I increase the wavelength, I increase the confinement, right? It's more confined.
No, it's the opposite. When you increase the wavelength, the waveguide becomes smaller from the wavelength on the wavelength scale. The ratio between you have a waveguide with a given width. If you increase the wavelength, it's like decreasing the width. So it's less confined. So it's a good approximation if C0 is the field coupling coefficient calculated at the wavelength lambda 0, the wavelength that you take as reference, around that wavelength, the behavior is linear. This is nothing strange. We have to expect that the coupling coefficient depends on the wavelength. You accept, right? No, right. So it means that the transfer matrix, so the behavior of the coupler depends on the wavelength. So the P cross, for example, is sin square of this expression. So this is a problem, in some sense, because if you wanted to have a coupler that operates over a large bandwidth, optical communication people like to work across 35, 40 nanometer, that is the bandwidth of the optical amplifier. So from 1530 to 1570 or even more. And if you want to make a coupler that works on this range, well, it's difficult because the coupling coefficient depends on the wavelength. So this is an advanced topic, and we do not enter how to design a coupler that is not very much sensitive to the wavelength, but keep in mind that there is this problem. Your coupler cannot be 3 dB at every wavelength. Or can be an advantage. So we have the dependence on the wavelength, so we can exploit this dependence. As an example, assume you want I can cancel all this part. Assume you want to enter here with lambda 1 and you want to enter here with lambda 2. Two signals with the two different wavelengths. can you think, or is a crazy idea, to use a directional couple to combine the two wavelengths and have the two wavelengths at the same port?
Like a mixer.
I don't know what you are thinking when you say mixer. If you think to the electronic, mixer is something non-linear. Mixer make a multiplication, while this one is a linear function, is not a non-linear, so it's not a multiplication, but is a combination. So I would call it a multiplexer. The right name is multiplexer. So P cross is this one, P bar is the cos square of this expression. And so we have to impose that P cross at lambda 1 is equal to 1. So we need this product at lambda 1 equal to half pi. So the sin square is equal to 1. So lambda 1 go to the cross and exit to this point. Okay?
Using the word multiplexer means that we cannot have them both at the same time. Because multiplexing is not having them, but combining is different.
Once again, I don't know what you are thinking when you say multiplexer. Multiplexer can be in the time domain or in the frequency domain. How do you call it? A device, and you have several signals that enter at different wave frequency or wavelength, and one output and all the frequency, all the signal at the same time exit from this port. How do you call it?
Multiplexer.
But usually multiplexer, we had a port to choose which of them to go out, not all of them. It was electronics multiplexer.
In the time domain. In the time domain. In electronics, a device that combines different signal at different wavelength and exit this port is called multiplexer, frequency multiplexer. The other one is a time multiplexer. This is a frequency multiplexer. You have polarization multiplexer, you have quantum multiplexer, you have a lot of kind of multiplexer. When I say multiplexer, I mean a wavelength multiplexer or frequency multiplexer.
Just on the formula CO lambda 1 on lambda, we are using, we are imposing the half pi because we want lambda 1 to go on the cross.
Yes.
The cross.
Yes.
But in this way, we don't change even lambda 2 that goes.
Now, the second condition, you are not happy only with this, but you want also that this at lambda 2 is equal to what? We want it in bar, so we want this equal to pi. With this condition, P bar is equal to 1 at lambda 2. So lambda 2 goes straight and arrives to this point. So this is a wavelength multiplexing. You can combine the two wavelengths, exit port from the same port. And this is the basis of WDM system. WDM system usually have tens of hundreds of wavelengths, so we need something like this that operate on 64, 128, 256 channel. So this is more complex, but we are just starting. So be happy of two. Okay? Be happy or not? I mean, can you solve this system? This is a system. We have two unknown, C0 and L, and two equations. So we should be able to solve it. Can you solve it or not?
Yes. Given the lambda 1, lambda 2.
Yes, sure. Given lambda 1 and lambda 2. Try to solve this system, if you are able.
No.
No?
There are infinite solutions.
No, there are no solutions.
No solutions.
Well, and then you have, this is the unknown. So it's one unknown. You remember that in the directional coupler, we have only one unknown. They appear both together. They are tied together. We wrote as the two parameters, field coupling coefficient and length, but are the same. They appear always together. So we wrote two conditions for one variable. It's not possible, unless you are lucky. So it depends on lambda 1 and lambda 2. But in general, you cannot solve it. So if you solve, you have C0L equal to half pi multiplied by 1 over lambda 1 minus lambda 2. So we have this condition. So if lambda 1 and lambda, so you have lambda 1 and lambda 2, and you find that this number. But the other condition is that from this one, 1 equal to 1, or that is, you find 2 equal to lambda 1 over lambda 1 minus lambda 2. So you see, if you choose arbitrarily lambda 1 and lambda 2, you don't get an integer number. So if the wavelengths stay in this ratio, you are lucky and you can find the solution. But if not, nothing to do. So, what is the conclusion of this thinking? The directional coupler, we know how it works. We know how to design. We know that it depends on the wavelength. So in case you wanted to operate over a broad range is a problem, but you can exploit this dependence. But it's not easy, it's not much flexible, because there is this stronger constraint. As a result, you get this satisfied if lambda 1 and lambda 2 stay far away one from each other. We can continue here. I write on the upper part, so you are more. Is 2 lambda 1 minus 2 lambda 2 equal to lambda 1. So we have lambda 1 equal to 2 lambda 2. So if you choose the wavelength like this, one double the other one, then you can find a combination CL that satisfies both equations and works like this. So if you are thinking through a WDM system, this is useless. You have always the channel very close one to each other. It's not possible to work, far away. However, there are situations in which this condition maybe is not true, but is a good approximation. As an example,
shouldn't be the opposite, like lambda 2 is 2 lambda 1.
If this is correct, it should be
I think
correct.
this is not correct.
Huh?
Because like, I think this is not correct. Because
This one,
I think it's so.
make relation of the two. It depends if you put lambda 1 and lambda 2 in bar or in cos. You can get one this, you can get this, or the opposite if you change lambda 1 and lambda 2. Let's assume that this is correct. So we have this condition in erbium doped fiber amplifier that some of you seen in the optical communication course. The amplification is obtained by propagating in a fiber, in an amplifying fiber, the signal at 1.55 micron and a pump signal, so another wavelength that is useful for the amplification, that usually is at 980 nanometer. So you see, far away is not, this condition is not satisfied, but you are not far from. So, if you, for example, enter here with 155 and you can get out with 155, you enter with 980. Some 980 exit from here, a small part, and most of the part exit from here. And you combine both. Not all exit from this, because this relation is not satisfied, but you are not far away. You would be satisfied with the 760, 770. So, this device can be used as multiplexer if the two signals to combine are very far away one to each other. In frequency or wavelength, yes. If not, it's not a good solution. We have to think to something else.
Because the solution, the one for the system is C0 times 7.
It is a unique.
So we don't want to find C0.
No, never.
One. I know for the matrix there is C0 times 7, but if you want to find C0 times 7, we can.
No, you have to choose one of the two and calculate the other. And usually you choose C0 because this depends on the shape of the waveguide, on the technology, on the refractive index, the distance of the waveguide, a lot of technological constraints. So C0, I say you can choose, but you cannot choose very much because it comes from everything else, no, from the waveguide.
You can only choose one.
Yeah, yes, basically. Basically, yes. You can choose, you can change a little bit C by changing the distance between the two waveguides. So we have seen the directional coupler as a device to combine things to combine a signal or to split. We started with the splitting 50-50, 10-90, 30-70, whichever ratio you want. We have seen, we discussed some problem related to the tolerance, to the accuracy of the technology, and then we investigated the dependence on the wavelength, and we tried to think if this device can be used as a multiplexer. The conclusion here is that yes, you can use as multiplexer if the waveguide, if the wavelength stay more or less in this condition. The closer you are to this condition, the better it works your multiplexer. But obviously, you cannot combine the signal at 1550 and 1551. It's not possible.
Can we use directional coupler as a multiplexer if in one of the waveguides we have several lambdas, I mean several wavelengths? If in one waveguide we will have several wavelengths.
If here you have many wavelengths,
is it possible? Is it worth? Does it worth?
If I draw the transfer function as a function of lambda of the directional coupler, assume this is a P cross and P bar, okay, is a sin function that depends on lambda. So is something like this. Okay, and the other one is so the period is not constant because depends on that. So what we are doing here is to place a channel here and another channel here. One in bar, the other one in cross. So this is the picture of this condition. So what we are trying here is exactly this. So if you have many wavelengths, well, it depends where you put the wavelength.
Is there also matching conditions for different, series of the waveguides, like microwave systems for transmission lines? Like several different waveguides, and between those two waveguides, are there matching conditions for the light or something to not have a
I don't know
loss?
exactly what you are referring to.
Ah.
We can maybe discuss separately this. So this conclude, I would say, the topic of directional coupler. We will continue to use directional coupler for the entire course, okay? But at the moment we stop here. I think we can do a short break because the next topic is other device to do the splitting and the coupling of different inputs. And then the next topic is use it to realize device.